Hi everyone. Today our lab will be involving the momentum principle or Newton's second law, and it's demonstrated in today's lab of an object falling from rest. So we have this equation here of final velocity equals initial velocity plus F net over mass times delta t. And in this scenario, F net over divided by mass equals acceleration, but we'll find that acceleration does not equal 0 because we have a changing velocity, so that there are forces acting upon the object, unlike last week's lab where there were basically no forces acting upon it. So we're just going to open up Tracker. I took footage of a stuffed animal being dropped from rest and uploaded the video to Tracker. And I set up the calibration stick and rotated the axis just to account for the fact that we have vertical motion rather than horizontal motion. So here's the graph that I got after pinpointing the center of mass of the object and just following along with. And as you can also see, I slightly tilted the axis because the video was taken from a different angle from the camera. And I just dropped the stuffed animal from the top and just let it fall and click the center of mass as best as accurately as I could. And I just use that information of the mass of the object and put that into Python to create a computational model. Okay, so with Python, I inserted the mass of the stuffed animal, which in SI units, so kilograms, 0.02835. I also set the initial conditions, initial position and velocity are both 0. Time is starting at 0 seconds. We have our time step as 0.001 seconds. And we account for gravity, 9.8 meters per second. We're not going to account for drag force just yet. We're just going to account for gravity at this point. And we're going to set the loop for less than 0.434 seconds, which is when the footage from Tracker ends. So we'll just loop around that in the computational model. We put in our data for Newton's second law, and then we will run and see how the graph looks. And here you can see the graph after we run the model, and we'll just account for drag and see how that appears. In this graph, we see that's downward sloping, just like the one in Tracker, and we'll just add the drag force. So we add drag force by using guess and check method to find a value called B that will yield the final position in the experimental data. So after using some guess and check, we found that the value 0.035 best yields the final position from the experimental data, where y is negative 0.78. So now we'll just run this and see how it's similar. So seeing right here, the vector at 0.434 seconds, which is when the experimental data ends, we have a y value of negative 0.78, which is exactly what we had in the experimental data. So this is much more accurate, accounting for the drag force. The graph is much more similar, and we can compare these on Google spreadsheets with the graph with drag force and gravity, the graph with just gravity alone, and the actual experimental data. As you can see, the graph with just gravity over-predicts the fall. It starts out pretty similar to the actual experimental data, but then it just kind of over-predicts. But the graph that accounts for gravity and drag, the red graph, that is much more accurate because of the fact that it's accounting for gravity and resistance. So the object is falling due to gravity, and the graph that shows drag accounts for the fact that drag force increases with velocity until a maximum velocity is reached, where drag force equals driving force. And this is where terminal velocity occurs, where drag force is equal to the driving force, where the force of resistance is equal to the force of gravity. So the terminal velocity is only demonstrated in the gravity and drag graph. It's not demonstrated in the graph with only gravity, because velocity is equal to the time times negative 9.8 because this object is falling downward. Now, if the object is thrown downward instead of being let go from rest, the terminal velocity is the same. It's just the drag resistance that differs due to the increase in acceleration. So the force compensates to reach that terminal velocity, but the terminal velocity is the same. It's just the resistance that has to account for that, because the gravity stays the same too. Like, gravity isn't going to change. So overall, we see that when we have a computational model, the one with gravity and drag is much more accurate to the experimental data.